Infinity.
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 What is infinity?
Infinity is really cool.
It's about as big as it gets.
You can't really put a name to it because that limits it.
Infinity, as I see it, refers more to the true nature of reality. No one and no thing has any kind of separate, inherent, or intrinsic nature.
I'm a librarian, so I feel that infinity is my business. I connect words that were written 1,000 years ago, also words that were written last week.
If there's an infinite number of possibilities, it means I have no limits as a composer or a performer. Every single note that I choose to play in a song, I could have played any of the other notes, or the notes between the notes, you know, like in the blues.
Infinity is something that just goes on and it's continuous. It does not have an endpoint.
I can show you my experience of infinity.
Infinity means numbers go on and on.
Infinity, generally speaking, is a very precise mathematical concept.
Infinity is a pure fiction, an optical illusion. Before Einstein, people believed that the speed of light is infinity, it's instantaneous. And then Einstein explained it into relativity theory, that the speed of light is finite. It's very, very fast, the light, but it's still finite. So analogously, the largest integer is very, very big, much bigger than the speed of light, but still finite.
What we will be talking about, we want to call a near infinity. It's something which actually does take place in our finite world, but it's so big and complicated that complexity of it is approaching infinity in practical terms.
Now that we have computers, it's time to get rid of this illusion and start and doing completely, purely finite and discrete mathematics.
Infinity is there to stay.
I've spent years thinking about it, and I'm no wiser.
No, Mom, I'm not an accountant. This is what we do. Right? We deal with stuff like that. We deal with questions like that. This is why people like me go into mathematics. We've got these different perspectives we're going to be investigating tonight. We've got infinity looked at from the point of view of philosophy, theology, mathematics, and physics. And we're going to try and wrap ourselves around all of that in the next 90 minutes. So sit back and enjoy the ride. Okay, we're going to begin with Philip Clayton. Philip's a philosopher, theologian. He's a provost of Claremont Lincoln University. He was a principal investigator of the Science and Spiritual Quest program. He's written more than a dozen books in this field, including Adventures in the Spirit, In Quest of Freedom, and Religion and Science, The Basics. And he's spoken about this all over the world. Philip, take us from what we've just seen. Thank you much.
Infinity, what an incredible concept. You can picture the earliest men and women staring up at the innumerable stars or watching grains of sand slowly slide through their fingers and think, what is this thing without limit? I want to take you on a brief little stroll through the history of the infinite. Try to do that in a finite period of time. 5 minutes?
Good.
Let's see if, yeah. Keith's going to watch me. Let's see if I can find a couple of philosophers, a couple of theologians, maybe a representative of East and West, to give you some sense of the parameters of this concept, if that's not a contradiction in terms. In some ways, a vast variety of ways of conceiving of the infinite. In another sense, a few core concepts that keep arising, that you'll see over and over again as we move through this evening. Let's start with Zeno of Elea, the philosopher who gets credit for first introducing the concept of the infinite in the West. Actually, that's not quite right, because Anaximander had introduced the concept a few years earlier of the boundless, apeiron, the thing that's without limits, a scary kind of notion that the Greeks really disliked. You can't build a Parthenon with the boundless, right? Zeno found that whenever he introduced real infinites into the world, he ran into paradoxes. So let's take the fastest Greek of all, Achilles, and let's set him in a foot race against a tortoise, right? Can we give the tortoise a head start? Is that all right? Right. So the tortoise is out there in front. An hour later, he's made 100 feet, right? And then here goes Achilles. Zeno says, well, he's got to go halfway to the tortoise first. And then he's got to go halfway between there and the tortoise. And then he's got to go halfway. You get the point? Achilles, Zeno argued, could never pass the tortoise if infinites are real, because he always has to transverse half the distance and half the distance ad infinitum, right, to the end. So the infinite and paradox are linked from the very beginning. Let's move on to Pythagoras. We give Pythagoras credit for inventing the notion of mathematics, which, by the way, in Greek means that which can be learned. He did it with a quasi-religious orientation. The Pythagoreans said that each integer has some sort of philosophical or spiritual meaning, and the ratios between the integers are crucial. 7/8, 1/4, and so forth. So the harmonic progression was for them a religious insight. He launches the idea of the theorem, and what's the most famous theorem from Pythagoras? The Pythagorean theorem, right? And all of a sudden, the whole project goes to hell in a handbasket, right? We've got an equal right-angled triangle, 1 and 1, so we see 1 squared plus 1 squared, 2, right, equals c squared, so c equals the square root of 2, but that is an irrational number. To write down the square root of 2 would take us infinite digits with no repeating pattern, right? Right in the middle of the religion of the infinite breaks out the impossible, irrationality, the religion of rationality shot to hell right at the outset of the story. Let's step over to India for a moment and see how things look different over there. We go to the great founder of the Jain religion, you know, Ahimsa, Martin Luther King, Gandhi, Mahavira. The Jains weren't famous just for that, though. They also did incredible speculation on the nature of the infinite. As far as we know, by 400 BCE, the Jains had introduced a notion that hadn't been used before, the difference between that which goes on without ending and the truly limitless, the truly endless. They also began to distinguish orders of infinite. So there's infinite in length, infinite in area, infinite in volume, and infinite perpetually. Get the distinction? They're trying to give us orders of infinite as they go. And the last thing for which we credit the Jains, when they distinguish between innumerable, innumerable, and infinite, they said the highest innumerable number, n, and they defined it the way that, as we'll hear in a moment, Cantor defined Alf null, the first number of the transfinites. So amazing comprehension in India some 2,400 years ago. All right, let's step back to the Greeks and come to Aristotle, the father of some 24 sciences, that crucial thinker. Aristotle realizes that with actual infinities, we are in deep doo-doo. Basically, physics is not going to work well. So what he decides is that there exist no actual infinites. We have to banish that concept from the physical world if we're going to do good science. So he says it's fine that we can have a potential infinite. It just can't ever be actual. So for example, the potential infinite is start counting upward. You can go as long as you want to, but in a finite period of time, you'll only make it a finite distance. The world is only a finite number of years old, he said. Therefore, there are no actual infinites. Take a quantity and start dividing. You can divide it as much as you want to, but at some point you'll run out of time, as I'm about to, and you have to stop. Aristotle launched this notion of potential infinite. All right, let's finish off with 3 theologians and 3 radically different understandings of the infinite. Let's go to the high Middle Ages, the scholastic period, and that greatest of thinkers, Thomas Aquinas. Thomas Aquinas says, as a theologian, I'm interested in a different question. Y'all are interested in quantity. I'm interested in a quality of existence. What mode of existence would God have, the divine? God would be qualitatively infinite, which means God would be ens perfectissimum, the most perfect being. It's a mode of existing, it's a way of existing that sets God apart from anything else, not quantity. So he bifurcates between the mathematical infinite and a religious or philosophical infinite. But still Aristotle rears his ugly head because even this infinite God couldn't create an infinite object because anything in the world must be by nature finite. Moving on from Aristotle to the 15th century, we find the Bishop of Cologne, Nicholas of Cusa. And here's a theologian who decides he's going to go with the infinite all the way, no restraint. So the infinite, what is that? It's that thing which has no limits. Therefore, everything must be included within the infinite. Nothing can be excluded. The world itself must be within God. Heresy, I know, it almost cost him his job. Mathematics love Nicholas of Cusa because he used mathematical examples to describe the God-world relation. So God is the circle whose center is everywhere and whose circumference is therefore nowhere. Nothing is outside of God. And he said, if you get that right, it means a coincidence of opposites. God, world. God, humankind linked together. And he said, we are the animal that stands at the boundary between the eternal and the finite. And finally, let me close with that great heretic, the one that the modern thought loved to hate, Baruch de Spinoza, a Jewish, fascinating Jewish philosopher kicked out of the synagogue at age 14 for allegedly saying that God has a body. Spinoza decided to write his metaphysic in the guise of geometry. Etica more geometrico. Ethics in the guise of geometry. And you guys, it's overwhelming, compelling argument. If God is infinite, God is the one substance. There can be no other substances besides this one. The substance must have infinite attributes. And we, finite little beings, can't be separate beings, so we must be modes of the one. God, however, is not the transcendent God, the personal God who does stuff. He used the phrase Deus sive natura, God that is nature. God and nature become absolutely one for Spinoza. And the highest ethic is for you to live in accordance with the laws of nature. To be a part of that one unfolding infinite whole is our fate. Half the philosophers revere him as science-friendly, half the philosophers revere him as theological. For him, it is the intellectual love of God to know nature, to know yourself as part and parcel of nature, and to behave together with nature. The infinite then focuses Spinoza from theology back into the natural world. So Keith, a short history of infinity.
Wow. Okay. It makes me feel nervous. I mean, we're live streaming this. I'm not quite sure who's listening in to this broadcast, but as a simple mathematician, I'm feeling very nervous there. And I'm going to very rapidly bring it back to my own comfort level, because my next guest is a regular practicing mathematician like myself. It's Stephen Strogatz, one of the world's most highly cited mathematicians. His honors include a Presidential Young Investigator Award, a Lifetime Achievement Award for the communication of mathematics to the general public, and membership in the American Academy of Arts and Sciences. He's currently a professor of applied mathematics at Cornell, and his publications include Nonlinear Dynamics, The Calculus of Friendship, and, wait for it, The Joy of X. Stephen.
Thank you.
Thanks very much, Keith, and thank you all for coming out. I'd like to, yes, as Keith said, bring it back to mathematics. And for us in the math world, the really great transcendent hero of infinity is Georg Cantor. Cantor lived in the mid-1800s and came up with ideas that are so mind-blowing and so stunning that we're still kind of reverberating from his insights. We'll be hearing about the disturbing things that he thought of that are still so counterintuitive that the mathematicians and physicists are really grappling with them even today. So the big insight from Cantor, the biggest of all, is that there are different kinds of infinity. Some infinities can actually be bigger than others. And so I want to walk you through a few of his mathematical arguments because they're so beautiful and so elegant that if you haven't seen them, I think they'll change your life. And if you have seen them, this is like listening to the greatest song, your favorite song, a second time. I don't think you'll mind. So, but to set this up, I want to, I'm going to show you some visual versions of what Cantor came up with. But first, I think it's worth mentioning a little bit about his life because it was, as with any great maverick, there were people who opposed him. He was not regarded necessarily as a hero to all mathematicians. In fact, one of the greatest mathematicians of his era, Henri Poincaré, described Cantor's work as a disease. Ouch. Another one of his colleagues, a mathematician named Kronecker, who was in a position of power in Berlin where Cantor very much wanted to be a professor. He never got to be a professor in Berlin. Kronecker wouldn't let him. Kronecker described Cantor as not only a charlatan, but a corrupter of youth. Now, I don't know what that makes me, since I see there are some young people here, and I'll be talking about his work. So, yes, corrupter of youth. Well, actually, this was no joke for Cantor, because he, as it turns out, suffered from mental illness. It seems that he had we know that he did have very significant bouts of depression, may have had bipolar disorder, and he spent quite a few stints in sanatoria. It used to be thought that it was because of these attacks from mathematicians that he was driven to this, but I mean, in more modern thinking, probably he just had, he suffered from depression, but it didn't help that he was taking this withering criticism from so many people. On the other hand, some of the other great mathematicians of the time, like a man named David Hilbert, probably equal to Poincaré in greatness as the two greatest of that era, Hilbert described Cantor's work as a paradise and said nothing will ever expel us from this paradise that Cantor has created. So let me introduce you to Cantor's paradise, first by showing you some of the paradoxes and really startling things that come about when you start thinking about infinity mathematically. And the way we'll do this is with a charming video that was produced by the Open University a couple of years ago.
60-second adventures in thought. Number 4, Hilbert's Infinite Hotel. A grand hotel with an infinite number of rooms, and an infinite number of guests in those rooms. That was the idea of German mathematician David Hilbert, friend of Albert Einstein and enemy of chambermaids the world over. To challenge our ideas about infinity, he asked what happens if someone new comes along looking for a place to stay. Hilbert's answer is to make each guest shift along one room. The guest in room 1 moves to room 2 and so on. So the new guest would have a space in room 1. And the guest book would have an infinite number of complaints. But what about when a coach containing an infinite number of new guests pulls up? Surely he can't accommodate all of them. Hilbert frees up an infinite number of rooms by asking the guests to move to the room number which is double their current one, leaving the infinitely many odd numbers free. Easy for the guest in room 1, not so easy for the man in room 8,600,597. Hilbert's paradox has fascinated mathematicians, physicists and philosophers, even theologians. And they all agree you should get down early for breakfast.
It's a brilliant video. I hope you caught the main mathematical points at the risk of over-explaining. I'm just going to remind you what you saw, that in Hilbert's Hotel, which is this parable of infinity, first of all, the Hilbert Hotel always has room, even when it's full. It has infinitely many rooms, and so as it was explained, if another guest shows up, you can still make room for that guest by shifting everyone over one room. And there's always room because there's infinitely many rooms for them, and then the new guests can go in room 1. If a bus, or as the video says, a coach, even a bus with infinitely many new guests,
is still not enough to cause trouble at the Hilbert Hotel, because you can shift all the current guests into the even rooms, leaving the odd-numbered rooms for the guests. So the question starts to become, well, if infinity is really that big at the Hilbert Hotel, is there any number of guests that you couldn't accommodate at the hotel? I mean, are there infinities so big that even the Hilbert Hotel would not fit them? And so Cantor worried about this and came up with an attempt to find an infinity too big even for, I mean, he didn't think in terms of the Hilbert Hotel, but let me illustrate it that way by imagining a situation that if you're kind of a nasty contrarian, you might think, what if an infinite number of buses, each carrying an infinite number of people, show up? What will the night manager do with this? So let me illustrate. In fact, that problem can be solved at the Hilbert Hotel. That's no problem at all. And so here's the solution to it. Let's first visualize these people by showing a picture which will have a row containing all the infinitely many guests that would correspond to bus number 1, and then there's bus number 2, each with its infinite number of guests, which I'm going to depict as faces. And then there's an infinite number of these buses. So there's the first image. It's not supposed to just be 4 by 4. You're supposed to picture it with infinitely many guests in each row and infinitely many buses.
The audience probably can't see, but from my close position, I can see some dots at the end of those rows, the infinity dots.
Yes, thank you, right. So those 3 dots are supposed to indicate that both the rows and the buses go on in all directions. All right, now, a first inexperienced manager might attempt to solve the problem this way. I mean, what the goal is to assign each passenger a room. And the problem will be solved if, for any given passenger, you can say, that person is in a room with a finite number, a specific number. Like, imagine a guest list, and I can say, oh yes, Mr. Smith, you're going to be in room 133. As long as everybody has a room, everybody's happy. Here's the first attempt to put people into rooms. Let me put person 1 from bus 1 in room 1. And then I'll put the second person from that same bus in room 2 and the third person in room 3. You can see this is not a good solution. Do you see what the problem is? No one in bus 2 is going to be happy. Because the whole hotel will be filled just with the passengers from bus 1. And so you'll have infinitely many busloads of infinitely many unhappy people. This is not what you want at your hotel. So that is not a good solution to the problem. But there's a much more clever way of doing it, which then does actually accommodate everyone. What you do, notice this zigzagging pattern of arrows. You start with the first person. That person gets room 1. The second person is at the end of the first arrow. So that would be passenger 2 in bus 1. Then you go down to bus 2, passenger 1. That person gets room 3. Just follow the arrows, and that's the order in which people are placed into rooms. Can you sort of see what's happening, how it's fanning out from the corner? And that will have the property that you can pick any person in that infinite array, and that person will be served in a finite time. They will have a room. So this is a way of actually accommodating infinitely many people in infinitely many buses in the Hilbert Hotel. This raises the, oh, by the way, I should say that there's the abstract version of this, which is that this shows that the fractions, the positive fractions, starting, well, not starting, but think about any fraction, 1/3, 1/5, 2/8, don't worry about lowest terms, 4/17. Any fraction you can think of would correspond to one of these passengers, like the person in bus 4 and passenger 17, that might be what we would call 4/17. I mean, there's a correspondence between the people in these diagrams and the positive fractions. And so this argument that I've given you here is essentially Cantor's argument for showing that the positive fractions can be counted in the sense that they can be put into what Cantor called a one-to-one correspondence with the natural counting numbers, the numbers 1, 2, 3, 4. That is, there's a way of listing all positive fractions so that we can say this is the first one, this is the second one, this is the third one, and every positive fraction will be at some finite place in that list. They're not ordered by size, by the way. They're ordered in this way that I just described with this zigzagging pattern. So the rational numbers, the fractions, are countable, meaning they can be put into one-to-one correspondence with the natural numbers, 1, 2, 3, 4, and so on. And this raised the question in Cantor's mind. It seems like everything he could think of is countable. Every infinity he could think of was countable. Or to put it another way, the Hilbert Hotel really lives up to its motto. There's always room at the Hilbert Hotel. Well, actually, though, in 1873, Cantor discovered an amazing example showing that that was not true, that there's an infinity that is so big that it would defeat the Hilbert Hotel, no matter how clever the manager is. And this has to do with the amount of infinity contained in a continuous line. If you imagine the number line, you know, the traditional number line that was tacked on the wall of your elementary school, and it shows the integers 1, 2, 3, 4, and there's all the space in between where all the fractions are and all the irrational numbers. That continuous line, what we think of as the real numbers, if the real numbers showed up at the hotel, there wouldn't be room for all of them. And here's the proof. This is Cantor's famous diagonal proof. He said, imagine that there was a roster, a sort of a guest list, and this was a guest list. It's going to be a proof by contradiction. I'll show that there's a real number that doesn't have a room. Here's a putative list where room 1 is assigned to this real number that's being shown here, 0.42, etc. And room 2 is assigned to some other real number. Don't worry about the details of the number. The idea is just imagine that there was a list of all the real numbers, just like we could list all the rational numbers. Maybe we could list all the real numbers. Well, Cantor's argument is no, because if there were such a list, and here's an attempt to show what it might look like, you then circle the first digit of the first number. I don't know if you can see, there's a little circle around that 4. And then you circle the second digit of the second number, 2, and the third digit of the third number, 1. So from that, you construct a real number, which in this case would be 0.421, and so on. That's not the problem. That's not the bad number. What we then do is change each of those digits in that number. Like the 4 that begins this number, maybe make it a 3, or just whatever you want, just change it. Or the 2, that's the second digit, make it something else, make it a 7. Just have some system, but the rule is you construct this number down the diagonal and then you systematically change its nth digit to something else. That is, if it's the nth number, its nth digit gets changed. And so by doing that, Cantor constructs a number which is not in the list, because it can't be the first number in the list because it differs from the first number in the first place. It's not the second number in the list because it differs from the second number in the second place, and so on. So by systematically going down the diagonal and then changing every digit, he has now produced a number that is not on the list. And this argument shows that, in fact, the real numbers cannot be counted. There is no list that can embrace them all. And so with that comes the question then, this very nagging question that we're going to be talking about next, which is, well, if there are now two kinds of infinity, the countable kind and this continuous kind, which is bigger, are there other infinities? And really more to the point, is there some infinity that's sandwiched in between them? Is there some infinity smaller than the continuous infinity but bigger than the infinity of the 1, 2, 3 variety? That's called the continuum hypothesis, the idea that there is no such infinity in between. It was Cantor's great conjecture, but he never proved it. Maybe Keith will tell us a little bit about his own experience with the continuum.
Yeah, because early on in my career, I actually went into set theory because I got seduced by what happened next. And here is what happened next. In 1940, an Austrian mathematician called Kurt Gödel showed that this conjecture, the continuum hypothesis, that there is no infinity between the natural numbers and the real numbers, Gödel showed that that conjecture could not be proved false. Okay, you might say, it means it's going to be true, right? Well, no, because in 1963, an American mathematician called Paul Cohen showed you couldn't prove that it's true. Can't prove that it's false, can't prove that it's true. It's independent of the axioms that we take for mathematics. And as a graduate student beginning in the very end of the 1960s, I think it was significant that this was in the 60s. People were high on all sorts of things, high enough to try and go into the infinity. There was the question of, you suddenly realized that we had a technique, Cohen invented a technique called forcing, that allowed us to construct alternative set theories, alternative mathematics, in which you could prove things true, not true, or neither of them. You could prove things independent. And like many mathematicians of my generation, I got seduced by that kind of question. And we used Cohen's techniques in particular, and some of Gödel's techniques, in order to investigate alternate universes. And it was a wild period, but it was a period that was eventually going to get tamed. And it was going to be tamed, at least I think it was going to get tamed. I would say it's been tamed to a large extent by our next guest, who's William Hugh Woodin. He's a set theorist at the University of California, Berkeley. There's a type of large, actually I should be careful, large cardinal in my business does not mean a large portly gentleman in a red uniform. That's his business. A large cardinal is an infinity. It's an infinity of a very large size. So Hugh Woodin has a large cardinal named after him called the Woodin cardinal. He's made many notable contributions to the theory of inner models and determinacy. I think of him as the mathematical equivalent of physics' Ed Witten, who's invented 21st century mathematics that dropped into the end of the 20th century. Hugh, take us from there.
Let's all sit. Thank you for that introduction. Thank you all for being here. So I've spent my life trying to solve the continuum hypothesis. Now, we just heard you can't prove it true, and you cannot prove it false. It doesn't mean it doesn't have a solution. It just means we don't have all the principles yet. And so that's the question. Are we missing the key principles, or are there principles defined that will enable us to determine whether the continuum hypothesis is true or false? Or maybe there's a much stronger version of Cohen's theorem that shows that there really is no answer. So really the fundamental question is this. We have this conception of mathematical infinity, and it's embodied in our conception of the universe of sets. Now, that's a human creation. Maybe there's no there. There's no up. It's just entirely an extrapolation of the world around us into a realm where there is no truth. And not being able to answer the continuum hypothesis is a direct challenge on this. It's the first question you would ask in the mathematics of infinity. And if you can't come up with an answer for that, what sense is there to the subject? So that's the situation. Now, I have to say, when you work on a problem that can't be solved, you're allowed to change your mind. That's the great thing about it. So 10 or 15 years ago, following one line of inquiry or an attempt to find new axioms, I showed there was kind of an ultimate solution along this line, and I speculated then in a series of articles that the continuum hypothesis was false. And in fact, there was exactly one infinity in between the infinity of the counting numbers and the infinity of the real numbers. And in any case, I showed there was an optimal solution. But then that solution ultimately doesn't fit into understanding the entire universe of sets. The continuum hypothesis is just one instance of an infinite sequence of questions. And it makes no sense to answer the problem of the continuum hypothesis without having some global solution to the universe of sets. So that became the problem. What could this global solution be? Well, we're at a crossroads right now. There's a series of conjectures, very precise, and the key question is whether these conjectures can be proved or not. If they can be proved, we will have one new principle which, when added to the traditional axioms of set theory, will settle the continuum hypothesis. True, so I'm a traitor to my previous self. And it will resolve all instances of the continuum hypothesis. And in fact, it will resolve all instances of questions which Cohen's method to date has been used to show are unsolvable. So that's kind of one holy grail. Prove these conjectures, we will have advanced our understanding of infinity, and we'll have a conception of the universe of sets that is as robust mathematically as a conception of the integers themselves. That's one possibility. The other possibility is that you refute these conjectures. Then it's utter chaos. We're back, it's much worse than where we were. So that's where we are. And I really am not sure what will happen. Many people have said, and they take the position that the fact that the continuum hypothesis could not be solved is an indication of this is all just human imagination gone wild. You know, and there is some merit to that. I don't believe it, but you know, I got corrupted by Cantor. So, on the other hand, if the other picture unfolds and we do prove these conjectures. Maybe we do them in 5 years, maybe we do them in 1,000 years, who knows? I think that will be a remarkable event, because set theory, you don't see it. There's no satellite you can build to go out and measure the continuum hypothesis. You can't go to Europe and say, look for this particle in the LHC. There's nothing in our world around us that's going to help you determine whether or not the continuum hypothesis is true or false, as far as we know. Set theory has not penetrated into physics yet. And if we see that this imagining of this realm far beyond the integers really has content and meaning, and our intuitions guide us to the true principles, I think that's remarkable, because it will be success where there was no reason to expect success. You don't find the answer to the continuum hypothesis by some clever proof. We know you can't do that. Somehow there has to be a solution that forms to our intuitions. There have to be clues. And there's no reason to expect that that will happen. It really could just all be a fiction. So there's this realm. It's beyond the realm we see around us. Does it exist? And one key question there is, if it exists, the continuum hypothesis has an answer, and we need to find it. Or we could go the skeptics route and show once and for all that the conception of mathematical infinity is just that, a fiction, and there is no answer. So those are the two futures, and I wait to see what happens.
Whoa. So hands up all those people who are attracted to mathematics because there's always a unique right answer. And it's in the back of the book. Well, it may be in the back of the book, but no one's managed to get hold of a copy of the book yet. So, it's worth remembering, by the way, that we got into this infinity business for very practical reasons, starting with people like, well, the people you mentioned, Archimedes, and then Newton and Leibniz, who'd invented calculus. Integral and differential calculus, the basis of all modern science, technology, communications, medicine, the basis of the world we live in depends on handling infinities. So we can't ignore them. These things arise from very natural and real considerations, which I think is a point where we need to bring back the physical world from which this mathematics began. And that's our final guest that we're going to bring on is Raphael Bousso. He's a physicist and a physics professor at the University of California at Berkeley. He's recognized for discovering the general relation between the curved geometry of space-time and its information content, as well as the landscape of string theory. His work has led to new views of cosmology, the multiverse of string theory. Raphael.
All right. Well, if you have no questions.
All yours.
Well, I guess we all went into our subjects in one way or another because of infinity. I think that that's true for me as well. We want to know questions like, is the universe infinitely large? Is space infinitely divisible? Can you look at shorter and shorter distances? And so what I'm about to say may strike you as surprising, but really the theme that I've encountered in physics is that when we see infinities, they signal that something's wrong with our theories. They signal a crisis, which is a great thing. Physicists love crisis. We love a catastrophe because it brings on a revolution. It means that something is deeply wrong with our theory. It's not just predicting, something a little bit off in some measurement, some small discrepancy. No, infinity. So infinity is never the answer to any measurement you could do. So you're way off, and something has to give. And there are many classic examples of this. One is the discovery of quantum mechanics a little over 100 years ago. In that case, the crisis in question was, people had figured out how to do thermodynamics. They'd figured out that hot bodies radiate. Like if you turn on the stove, you can see it glow red after a while, or the lamps, they radiate. They emit light, but you could calculate how much light they should emit, how much power is emitted by a lamp. And the answer was infinity. The answer was infinity, basically because there are infinitely many ways that the little atoms inside the material that's hot can wiggle. They can wiggle in particular in very, very fast ways. And every one of these ways will be turned on if you turn on the lamp, and then the lamp gives off an infinite amount of energy, and that would be a problem because it's not true. And so people had to do something about it, and literally quantum mechanics was invented as a desperate fix for this. I mean, Planck, who came up with the fix, the fix was that energy can only be emitted in certain packets of a certain size, which effectively turns off a lot of these wigglings. The ones that wiggle very fast don't get to wiggle anymore. He was a very conservative physicist. He hated doing this sort of thing, but he had no choice. And that's a wonderful example of how a crisis, of how a catastrophe in physics can drive us forward and make us discover new things. Another example I want to mention just briefly is what happened afterwards. People discovered how to apply quantum theory to the forces we know, electromagnetism, the weak and strong nuclear force that hold the nucleus together or sometimes make it fall apart. The theories that do this are called quantum field theory. And initially, these theories were also plagued by infinities. You started doing a calculation, after a while, out comes infinity. And again, of course, you're doing something wrong. In this case, it was a much more subtle problem. And it took people decades to understand how it really worked. But in the end, this property of being able to get rid of infinities proved to be incredibly constraining. It helped us zoom in on the right theory and know right away which ones couldn't be right. And in fact, this theory that was so dramatically confirmed recently, the Standard Model with the discovery of the Higgs that was already mentioned, you may have heard about it, this particle they discovered at CERN in Switzerland. People have believed that theory for a long time because there was other experimental evidence for it. But 40 years ago, when it was put into place, the reason that physicists really started believing in it was that somebody showed that you can get rid of all the infinities in that theory. That was an incredibly difficult thing to show. It's a very rare thing to happen in these kinds of theories. And so at that point, you kind of knew that you were onto something. So that's the setting. And what I want to tell you a little bit about now is that we still have trouble with infinities. And it's still incredibly exciting. And I think it's still, we still have these examples of problems which are catastrophic. I mean, we get answers which just are completely nonsensical and which are hopefully going to lead us on to some dramatic revolutions in physics. And so I want to come back to this question of how large the universe is. It's very large. But we've known that for a long time. I'll tell you in a minute what that has to do with the universe. This is Angels and Devils, out of respect for my theologian colleague here. Okay, but let me back off of this for a minute. So you've heard the universe is large, okay. You've all heard the universe is expanding. That's fine. Now, the question of whether the universe is infinite or not, it used to be phrased as a question of, let's look at the universe right now and think about how far does space go, okay? And, it's probably not going to end somewhere where, you fall off into nothingness. But one thing that it could do is it could sort of close back in on itself like the surface of the Earth, except without the interior of the Earth. You have to think that away. But it could be finite in that sense, or it just could keep on going forever. Now, that is a very hard question to decide. We could have gotten lucky if the universe is small enough that you could see light going once around that surface. Then you could really detect that it's finite. But the universe is only 13 billion years old. Light could only have gotten that far since the Big Bang, and so it could be finite spatially, but we just wouldn't know about it because we haven't seen. It's just like somebody who, like Kant, who never traveled outside his hometown. He has no idea that the world is actually finite. It could be going on forever. Who knows? But the terms of the debate have changed. The terms of the debate have changed. We don't need to be able to answer that question anymore. We don't need to know whether space is finite or infinite. And the reason for that is that things are happening in time, which are very interesting. So the universe is expanding, but what's new is that it's expanding faster and faster. That's new both in a human sense, it was discovered only about 15 years ago, and also in a cosmic sense, it only happened about 7 billion years ago. So it hasn't been accelerating. That's when it stepped off the brake and stepped on the gas pedal. That's when the expansion went from slowing down to speeding up. And now we see it speeding up, and it'll speed up at an exponential rate, meaning that it'll sort of double every few billion years. It'll double in size.
It's like the budget deficit, right?
It's like the budget deficit. And
that's the other kind of inflation, I guess.
Right, and it leads to a crisis. Just like, right. So now I'm going to tell you what happens. This is a painting by Escher, actually, but it's the universe, okay? And the beginning of the universe is the middle of this disk, the center. And then time goes outward, okay, to the edges. And what you're seeing here is the doubling of the number of angels and devils as you go forward in time. But in order to show this in a finite picture, I had to shrink. So there's really an infinite amount of time as you go to the edge, okay? And then you can kind of see that there's infinitely many angels and devils as you approach the edge. I had to rescale them, but you're supposed to think of them as all being the same size. What's happening in our universe is very similar. Regions like ours are produced over and over and over again in this very large universe, which is doubling in size all the time. We call this eternal inflation, literally like in finance. And the problem here is that you see, even if you can draw a circle here that represents the universe at a finite time, the circle is finite. I'm not assuming here that space is infinite to start with, but it gets infinite later. It gets arbitrarily large later on, and stuff keeps happening, okay? And that's the reason that this is a crisis is that it makes it very hard to predict anything, and here's why. One way to see this is to think back of Hilbert's hotel, which conveniently you guys already talked about. It may look like there are infinitely many angels or devils. Think of them as different regions in the universe, and you want to predict, if you open your eyes, where do you find yourself, in a black or in a white region? Well, there are infinitely many of both. It doesn't make sense to say it's a half-half chance, because I can reorder these angels and devils so that there's still infinitely many, but it makes it look like there are far more angels and so on. So I can always reorder this. In this universe, there are infinitely many places where you win the lottery, and of course, infinitely many places where you don't. And on what basis, then, do we predict that you probably aren't going to win the lottery? Right? Now, the lottery question, okay, we can laugh about that. We all know what the right answer is. All that this is saying is that we don't know how to recover the right answer from cosmology yet. Okay? But there are other questions, like what we should see when we look out through our telescopes, for which we need to know the answer to that question. And if something like the multiverse of string theory is right, there are many different ways that the laws of physics could behave at low energies. And to predict what we will see in an experiment that tests those laws, we need to solve this problem. We need to get rid of these infinities. Now, one thing I haven't told you yet, the same discovery, this was a colleague of mine at Berkeley, by the way, and some other people, Saul Perlmutter, who discovered that the universe is accelerating its expansion. It has another fascinating consequence. So it leads to this universe that becomes arbitrarily large, but actually there's nobody inside the universe who can see the whole thing. And I don't just mean us, we can't see everything because we live only, 13 billion years after the Big Bang, and so light hasn't had that much time to travel yet. No, even if you imagine that you got to live as long as you wanted, light cannot ever get to you from beyond a certain fixed distance because of this rapid expansion. It's very similar to the effect that prevents light from getting out from inside a black hole. Inside a black hole, space is collapsing too rapidly for light to outrun it. And here the universe is expanding too fast away from us for light to run back toward us. No matter how long you wait, it's not going to make it. Now, what I want you to think of these spheres as representing, other than really awesome graphics that think of one of these spheres, if you want the one with the zeros and ones on it, as what we can see, so what physicists would call your past light cone. Everything that could have reached us as long as it stuck to the rules and didn't go faster than the speed of light. That is bounded by a finite sphere. of a few billion light years in radius. Right? And that's all we can see. That's our universe. Right? That's finite. What if the right way to think about the universe is to say that really all this hypothetical stuff that our equations is telling us that nobody can ever see even in principle because of these limits from causality, because of the finite speed of light. What if that is just a fiction of our equations? What if the real thing that we should worry about is what one observer can in principle see? And again, I don't necessarily mean a limited observer like us. We're all going to die. The sun's going to burn out and so on. I mean, in principle, consistent with the laws of causality, what could you see? That's finite. And in fact, it's so finite that it even solves this problem of infinities that come from short distances. And I want to close with a brief comment on that. The reason I put all these ones and zeros on that sphere is to sort of indicate that there's a finite amount of information that you need to describe everything that's going on inside the visible universe. This is something that we've learned by studying black holes. And the reason it is so is that we know how much information fits into a black hole. We learned that from people like Bekenstein and Hawking, and that would be an evening by itself. In fact, we've had some here. We've learned how much information a black hole carries. And we also know that information cannot get lost. And we could convert everything in the universe into a black hole, which wouldn't be larger than this big sphere that's in our past light cone, the biggest sphere we can see. And so we know that there's a maximum amount of information that can completely describe the state of every single little detail in the universe. Not just where you're sitting, but where every atom in your brain is and what it's doing and where it's moving. It's a very large number, but there's a big difference between a large number and infinity. And this large, if you care about it, it's about 10 to the 103 bits. 123 bits, sorry. So it's a large number, but it's finite, telling us not only that we are able to predict again who's going to win the lottery and that you're not going to win it, but also that at some level space must be not continuously divisible. And we think we sort of know what happens when you try to probe distances that are too small, you start making black holes. But that's, again, that unfortunately is probably something I won't be able to get into. But I want to leave you with this. So far as we can tell, all that you ever need to worry about in the universe is finite. This bound on information tells us that you couldn't write down a single one of these numbers with infinitely many digits that appeared on some of the earlier slides. They do not have room in our universe. You would make a black hole that doesn't fit. So that's it. Thank you. Well,
so the question that's probably on your mind is, are these four guys talking about the same thing? And Philip, you live in Los Angeles. You negotiate the Los Angeles freeways on a daily basis. Can you pull all of this together, or is it really a black hole like Los Angeles? Whoa. I live in San Francisco. There's a thing going on here.
Well, Keith, it's a great question because the first response as you listen to the four talks is there are at least three different subjects being talked about. So we have the question of a mathematical challenge, and Hugh actually describes it as a purely mathematical challenge and separates it from the kind of question we'd face in physics. You did that explicitly in your talk. Then we have the physical challenge, powerfully expressed by Raphael. And then we have these broader philosophical or metaphysical questions that preoccupied the thinkers that I described. And the scary first response to these panels is, we've got three different spheres, like your different spheres, could it be no contact between them? That'd be bad news for the moderator.
Well, I didn't want to sound so negative. In fact, I should be careful. I said that infinity is usually a sign of crisis in physics, but that's really in the context of situations where we expect a finite answer. We want to get an answer that corresponds to a measurement we can make. Surprisingly often, structures that were invented by mathematicians for purely abstract reasons, for the fun of it, they get to make stuff up and then study it And they come upon these really rich structures, and then, 50 years later, 100 years later, turns out the physicists need them desperately to describe nature as we see it. And usually the mathematicians are faster, and they already have them, and they give them to you. And it could be that by studying questions such as the one that Cantor's continuum hypothesis, that you come upon a structure which later, in some way or another, has an application in our description of nature. What I don't think is going to happen is that the answer to any question that has to do with a measurement is ever going to be infinity. But that's a separate issue, and that's what I focused on. But I don't think that there's necessarily no connection ever between what you guys study, the structures that have to do with trying to make sense of infinity, classifying infinities. Who knows?
Let me go back to Hugh, because in your business you talk about the universe of sets. Is there any way that works as a metaphor for the kind of thing that Raphael talks about? Well, how far can you push that?
Depends what agency I'm talking to. Look, I have to be honest. It's a losing game to say one area of mathematics will not have future application. You just look at what's going on now. Who would have thought that esoteric questions in number theory from 50, 60 years ago would have fundamental societal importance in cybersecurity? So you never make that prediction, you'll lose. All I can say is that if the kind of infinities we study in set theory, if that whole apparatus does somehow eventually become relevant to physics, it'll be extraordinary. I mean, there are mathematicians who think it's not even relevant to mathematics. So we're just waiting to see the relevance to mathematics before the relevance to physics. I mean, but I'll push back on that in the following sense. I mean, it's one thing to have a great success in mathematics if that success leads to physics. And some will say that's the essence of mathematics, and that's a success of mathematics. But if a line of investigation in mathematics that seems so alien, so utterly removed from physics, can be successful, then that's something that's interesting. And that would be my position. If we are successful in the study of infinity and we can really answer these questions, and this is not a matter of calculation. There's no computer you can build that's going to give you the answer to the continuum hypothesis. It's not a simple matter of a calculation. It's a matter of trying to understand the concepts. I never write equations down. And so I get very strange looks when people see me working, and then they move away. I remember once when I used to work on the floor, and my daughter would sit next to me, and she'd start copying every mark that I made on my page.
Can you explain, by the way, just people, I mean, what are they seeing in this picture? This is how the sausage gets made, by the way, the mathematical sausage.
I get asked about these kinds of things a lot.
I just asked you again.
Yes. So some people are convinced I have a private language, and that, I mean, I know what I was thinking about. That's from last week, but I'll be truthful. I once watched someone, a mentalist who could really do these incredible calculations, and they would occasionally say the number that would park that number in a different part of their brain. And then I find I do that sometimes if I'm working on the computer, not that, and I have to remember a number that I have to type in another window. I just say it out loud. And then I can do all the other manipulations, and somehow I'm able to retrieve that 10-digit number. So what I'm doing there, I think, is I'm parking concepts, organizing them in my field of view, as I'm juggling various things. So I'm just parking complicated concepts on various marks. But, I'm not a biologist. I'm not a neurologist.
So this is a mathematical equivalent of diagramming sentences, or?
Well, I don't know. I mean, it's, that's what I do.
Yeah.
Wow.
And remember, if you're paying taxes, your money is supporting this.
Yes. I did have a question about line 14 in the calculation there, right? Are you sure about that one? Actually, though, there was one thing that occurred to me in all of this, which may surprise people, that within the sociology of mathematics, set theory occupies a somewhat possibly surprising place. That is, I'm a working mathematician who works in areas.
Element, I think.
Well, that's a nice, not such a nice way to say it. These people in set theory strike us, even in math, as sort of strange. That we.
Now it gets interesting.
It's true that we ignore them, and we know that they're doing really deep, important work, and in principle, it's foundational work. That is, they're shaking the foundations, and we're all working up on the second and third floor, and if they mess something up, it could actually tip us over. But we still ignore them, just trusting that this is irrelevant. But we may really be desperately wrong. It's a scary thought to operate that way.
I mean, okay, I'll respond to that slightly.
I think you have
to. I mean, set theory can be falsified. This entire, I mean, it's one thing to say we're not going to solve the problem, but you could actually do quite a bit more. You could show that the concepts are contradictory. Now, this can happen. This is Gödel's second incompleteness theorem. Any axiomatic system is subject to the possibility of being refuted. Now, if the axioms for number theory were shown to be contradictory, that would be a crisis, because that would wipe out all of mathematics. It would wipe out foundations of physics. Now, that doesn't mean the world's going to collapse, but that would be a problem. So if you want to gain security, it's kind of like mathematics lives in a stable island, and we have a solid foundation. And then there are the wild lands out there. That's infinity. You know, myths and things. And is it there? How secure is this? Can we build a city over there? So by investigating infinity, and to the extent that we can be successful, I think we make the case for the consistency of arithmetic. Now, that's a bit of a fanatical statement, but if infinity doesn't lead to a contradiction, certainly the finite isn't going to lead to a contradiction. And so maybe by exploring the outer reaches to see if there is a contradiction, you gain some security. So in that sense, maybe there's a value. I mean, you know, a finitistic contradiction would be really bad.
There's another...
Now everyone's moving away.
Doesn't get much worse.
I'm going to ignore that. Okay. In the sense that, you know, it is too horrible to contemplate that arithmetic is not. I mean, it happens to me all the time that my arithmetic is not consistent, but that's another issue. There is one place in physics that where I'm worried, or maybe hopeful in a way, that infinity is centrally important to it, but it's really not clear which way it's going to go, and that's quantum mechanics itself, and particularly the sense in which quantum mechanics is a scientific theory. It's a scientific theory because it makes statistical predictions. You know, where depending on how you prepare an electron, you can't say that you're definitely going to find it over here. You will just say, okay, if I prepare it 1,000,000 times like this, I will find it approximately 20% of the time in this interval and 30% in this one, and so on. And if you repeat the experiment 1,000,000,000 times, then the distribution you'll find will confirm the prediction even more accurately. And you can keep going. But of course, really, there's always an incredibly small chance that you just got lucky with your experiments, and actually the theory is wrong. That chance gets smaller and smaller as you repeat the experiment over and over and over again, but it is just a statistical prediction. So it could be that your theory is actually wrong and you're not discovering it. You're not discovering this contradiction because of some statistical fluke. It's just like sometimes, you know, you flip a coin 100 times, it always comes up heads. Could happen, right? So flukes happen, and for this reason, you might be concerned that quantum mechanics fundamentally doesn't make sense unless you are, at least in principle, able to repeat an experiment infinitely many times. Again, that's not going to be us, that's for sure. But what makes you worried, or should make you worried about the picture that I showed you, is that it looks like in our universe, even an observer who had an arbitrarily long lifetime could not repeat an experiment infinitely many times. That's not just because the accessible region and the causally accessible region will always remain a finite-sized sphere and everything inside it, but also because the universe is at a finite temperature if it's at a finite size, and it will not allow you to exist forever, even if you are not human and tied to all these constraints. So you cannot even in principle repeat an experiment infinitely many times. I don't know whether we should read that as a sign that maybe quantum mechanics is, after all, only some effective theory, some approximation to a richer structure that we have yet to discover. Or perhaps we could see it as a sign that it is possible in this universe for a kind of decay or a change to its state to happen, which does open up the skies and let you repeat experiments infinitely many times. Again, not you, but at least somebody in principle. Unfortunately, the multiverse of string theory, which played a big role in giving rise to these pictures, at least making them more interesting to us, it sort of tantalizingly gives us no answer about this question. It seems to contain in it regions in which the sky opens up and becomes infinitely large. We could decay into one of these regions. It would wipe us out, but it would then open up a huge amount of space and time in which maybe you could try to make sense of the laws of quantum mechanics at a completely rigorous level and no longer have to hope that in repeating your experiment many, many times, but a finite number of times, you didn't get unlucky and nature fooled you. So that's one place where I can one day perhaps see infinity enter as a real player in how we try to decide between theories.
You know, do you want to say?
Actually, yeah, I'll say something. So the physicist is opening the door to infinity. What if the theologian shuts it down? So what if the notion of infinity turns out to be something that only works if we never imagine it actually to be actualized at all? What if it's about epistemology? What if the notion is about the limits on what we can know, period? So get rid of the theological stuff, get rid of all the metaphysical stuff. And Hilbert did this actually in a lecture in 1917. What if the notion is about our trying to grasp some set of data or some set of events in the world and succeeding or failing? What if the interesting thing between us is that there are interesting cognitive similarities between what Hugh does for a living, what you guys do for a living, what a classic philosopher might do, namely taking something to be understood, grasping it to some extent, failing to some extent, and we're trying to get some measure on where we succeed or where we fail. And now I'm trying to imagine a meta perspective above the three fields represented in these opening lectures, something about the cognitive styles that humans have as we grasp for understanding around this.
Let me add to that, because by the way, we saw that video at the beginning, with all of those interviews. We saw it for the first time just before you came in. And I was struck by Zeilberger, the guy with the cool T-shirt, who mentioned the fact that with modern computing power, a lot of the needs for infinities disappear. I think he was referring to the fact that a lot of historical uses of infinity were because we were trying to grasp complexity with paper and pencil. When we have massive amounts of computing, and maybe, Steve, you're the first one ought to pick this up, with massive amounts of computing, a lot of that need for infinity, because the infinity, it was like standing back from the television screen. If you're too close to the screen, all you see are the dots. You stand back and it looks continuous. You've made the transition to the continuous, to the infinite. So a lot of those infinities were because we were trying to grasp with complexity. We have computers that can handle that complexity. Are we going to see that some of these infinities literally disappear?
It's a very interesting question, and I feel ambivalent about the finitist position that Doron Zeilberger expressed. Because it is true that we can get great insights from computers, which only carry finite amount of information in them. But I think I would like to bring in another subject here, which we haven't talked about much, which is art. I mean, I really think that there's an aesthetic reason in favor of infinity. That infinity not only is beautiful, but is simple, which might come as a little surprise to the audience members. That is, there are great simplifications inherent in pretending. I mean, whether infinity is real or not, like from a very practical point of view, it's helpful to pretend that infinity does exist. As you said earlier, Keith, calculus is based on the domestication of infinity. That we can tame infinity, make it work for us, pretending that a curve is infinitesimally, is as smooth as we like, and not just made up of lots of little straight segments, gives us a nicer mathematics. It's just, that is, if mathematics is something that people do to get insight from, as opposed to just something that machines do to get the right answer, we get a lot of insight by pretending that infinity exists. So in a way, I don't really care that much whether it does or it doesn't. It's more beautiful to pretend that it does, and actually more practical, as long as we're the ones doing the mathematics and the science. When the machines take over, like in the Terminator, then we may live in a finite world, and then, yes, maybe it'll all be, infinity may be gone at that point.
But if you want to know how simple it can get, arithmetic of the infinite numbers gets really easy. Adding two numbers, it's just the biggest one. Multiplying two infinite numbers, it's just the biggest one. There you are. You can do all your arithmetic homework with those two facts if the numbers are infinite.
Exponentiation has a problem.
I was leaving that one out because that takes us back to Cantor.
You know, there's art, but then you could also think of the role of the infinite and whether it's there or not in, say, ethics. Let's take human free will. So we know that a biological system produces some level of complexity. The next more complex biological system exponentially compounds that complexity. Move on to a being with, say, 10 to the 11th neurons and 10 to the 14th neural connections, say Homo sapiens, right? Now there's a very large range of behaviors that we could engage in the next moment. Just take the 4 brains here, multiply the possibilities, right? And the audience could be really surprised, you know, at what could...
1, 2, 3, 4, 5.
I'm not telling you who I admitted.
Someone missing one?
Mathematicians can't count.
The moderator is not allowed to play.
Oh, all right.
Okay. But think of the difference between that asymptotic increase in complexity and actual metaphysical freedom, that given the state of the universe at some moment, you, Steve, could do either this or not this, no matter what the whole causal chain behind. That's the leap from the asymptote to actually being what we call metaphysically free. And some of us in the audience would say, that really matters. I want to know if I'm a really complex machine or if I have this kind of pure free will. Now, I don't know the answer, but I have the sense inside me that that question matters to me as an atheist.
Does any theologian think that humans are metaphysically free? That sounds like heresy. I would have thought God was the only infinite.
So lots of theologians and philosophers think that there's a real
This is
freedom.
a different evening topic.
Different, excuse me? Well, we've got the theologian here. We might as well talk to him.
No,
But I mean, it's one of those questions, I was thinking about your last answer, Steve, one of those questions where the difference between an asymptote and that infinitesimal difference might matter immensely to the agent herself.
I think what we're seeing in all of these questions is that there's a big difference between a large finite number and infinity. And we're interested, I mean, as you were pointing out, for all practical purposes, infinity is a very good approximation in many cases to large finite numbers. When we say, you know, you draw a circle, well, you know, there's no perfect circle in nature. There's no, you know, number with infinitely many digits that we could actually write down. We know that just based on what we know about physics, about the laws of physics. It's just not possible. But science, to a large extent, is, you know, trying to make quantitative predictions to a very good approximation. And when we go from one theory to the next, it has to reproduce all of the old stuff, and it's just going to get a few digits after the decimal better, even if the theory itself is a complete revolution. And so we are in this business of making better and better approximations, and infinity has been an incredibly helpful thing for that. But at the end of the day, we also care about these qualitative questions. Is space infinitely divisible or not? Is the amount of information in the universe in principle unlimited or not? What we do with that information, you know, you probably go away, take away some other lessons than I would take away from that. But I think it's good that we have the ability to learn the answer to these more mundane questions by studying nature, by studying how nature behaves, and seeing that, okay, we certainly don't have an infinite amount of information in the universe. What we do with that is a separate question. But I think it helps, and it's qualitatively it's a huge difference.
We have just over 5 minutes left, and there are 4 people, as we've just determined. So starting at this end, I'll leave you till last. We'll start at that end, and everyone has basically 1 minute to make their final remarks before we we'll let everybody out of here. There's no exam tonight.
It's a MOOC.
Okay, I'll tell you about another infinity. I told you that if you try to probe smaller and smaller distances, well, the reason we built CERN, right, and these huge accelerators is that you have to smash things together with a huge amount of energy in order to probe shorter distances. This is how the uncertainty principle works. You need a lot of energy to resolve short distances. And then what happens is, if you had enough money to build a much, much bigger accelerator that goes, many orders of magnitude higher in energy, eventually you'd start making black holes. And then as you crank up the energy more, you'd make bigger and bigger black holes. And so there's sort of a minimum distance scale that you can get to, which is called the Planck length. And this thought experiment is a nice way of seeing why you can't get to smaller distances. You can try to devise more clever experiments, but they'll all lead to the same conclusion. But now make a big black hole and jump into it. And when you jump into it, space is contracting underneath you. It's kind of like the Big Bang in reverse. You get to a region where matter becomes denser and denser. You could be sitting on a collapsing star, for example. It's going to get compressed more and more, and the density becomes infinite. Einstein and his theory of gravity tells us that space becomes infinitely strongly curled up as you fall further into the black hole. This happens in a finite amount of time. You reach this point of infinite density. Of course, we know that that's nonsense, because at some finite density, we're leaving the regime where we can trust the theory. We know we have to replace the theory with something else. We need a theory of quantum gravity. We have to be able to describe something small, but also with a lot of mass at the same time. This is what several people, including myself, spend their life trying to do. But it's another example where an infinity is basically leading the way.
Hugh.
Well, so these infinities are all very small.
That's right.
I spent my life in, infinities really, really big, and people ask, well, you really believe in them? They're all falsifiable, right? They could be refuted. In fact, there have been mathematicians who have claimed to have refuted some of them. So I make my prediction as I've made before. I picked one. Now, there's an infinity named after me, so I picked that one. And I said, if this infinity is falsified at any time, I will resign my position. So there you go. I'm making, I put my academic life in behind this. But even though that's a frivolous thing to say, I have said it and I will do it. Now, as I get older, it's less of a... but the fact that we are able to come up with these principles that stand the test of time, so I would make the prediction these won't be refuted in 10,000 years, that's a prediction about this universe. Well, how does one account for that? Unless it's a reflection of something that's meaningful. So I leave you with that.
Yeah. Nice.
I'd like to bring you back to the first infinity you may have ever thought about, which was, if I think about my own children, there's a plate in our kitchen, which is supposed to be funny, a pie plate. You may have one in your house. It's a pie plate, but it also has the digits of pi written around it, 3.1415. And so when my kids see this, and there's lots and lots of numbers on this plate spiraling in towards the center, this gave them their first glimpse of infinity. So when many people think of infinity, they think of the mystery of the number pi, that these digits go on forever, they don't repeat, and they seem in some ways unpredictable. And there's something to me so delicious, I mean, kitchen puns aside there, something so delicious about the nature of a number like pi or other real numbers. I mean, pi is typical of real numbers in this way, that it has this infinite amount of unpredictable information in it. And that at the same time, it is so totally predictable. I mean, there is nothing more orderly. A circle, which pi embodies, is the very symbol of order and perfection. And so this coexistence of perfect predictability and order with this tantalizing mystery of infinite enigma built into the same object, to me is part of the pleasure of our subject of mathematics, and I suppose of infinity itself.
Beautiful closing. Beautiful closing. You know, what's really sad is you can see mathematicians grappling with the complexity of the question. You can see physicists grappling with the complexity of the question to the very limits of what the human mind is capable of. And then you see religion in the world today, Carl Sagan made this point in Pale Blue Dot, satisfied with a notion of God so simple and non-complex, not stretching us in the way that Steve's answer just did. And you think, wait, there's got to be something wrong with that. So I'd call for a philosopher or a theologian or a religiousness or a spirituality, let's just stick with that word, that would fight for that sense of something, what did Wordsworth say, something far more deeply interfused, that's worthy of an animal, of a species, that can grapple with the continuum hypothesis, that can grapple with finites and infinites in physics, that can think of its own ultimate fate, or whatever that ground of all things is, with not less complexity, and not less profundity, and not less open-endedness than we've seen from my three colleagues to my left on the stage. If human beings could do that, maybe it wouldn't be shameful to include philosophy alongside mathematics and physics in discussions like this.
Thank you.
I'm going to let that be the last word, because that was the way to go out.
Nice.
Okay, thank you all for your time.
Thank you.
Thank you.
Well, these are people who have